Shall we go ahead and get started? Right. And that's the last one. Enter from this door. All right, good afternoon, everybody. It's usually, I guess, Jaime is introducing our speakers, but today he asked me to introduce a good friend. I think you read his bio, so I'm not going through his bio, but definitely you can ask him during the students' meeting with him, how can he get a degree and in 3 years he became a full professor. So that tells a lot about him, right? So I'll start it with just that. Away from his bio, which you all can read, I think he's a special speaker for several reasons. One, I think that he's by far established the best laboratory in Latin America. And I encourage all of you to go and visit. We have few people from Latin America here, so they can testify. His lab is amazingly equipped. He has the right staff, and it's not just he runs the right experiments and shares his information. There's other important things that he's lending himself to the profession. And I would say that when it comes to the pavements, it's my own opinion, and many agree that he puts Latin America on the map, because he goes to several countries trying to educate them about pavements, try to praise the way that we are doing our pavement analysis and design. So he's in the road a lot, and that's definitely, it's a lot to his credit. And it tells us that we have a mission as a professors, as a students, is to share the information. And I cannot see that there is a better person than Louis who has done that. So I work with him on technical committees, on journals, on conferences, and I can tell you he's a very, very special profession. And I'm very, very pleased that he accepted our invitation. So I will turn it to you, Louis.
Well, thanks a lot to Dr. Arcadi for the invitation. And I am deeply honored to be here. I know how important has been this university for pavement engineering in the world. So I'm pretty happy to see Dr. Thompson here, Dr. Tutunluer. I've met him several years ago, also Dr. Rosler, and Hassan. We've becoming friends in the last years, working together also in a scientific committee and also in a special project in life cycle analysis. And of course to Dr. Alcadi. We have established a very good relationship for the last years, and we're working together also, as Dr. Alcadi mentioned, in several different things, and also trying to give the knowledge of not only of normal pavement analysis and design, but also life cycle analysis to Latin America, where we basically have done nothing till we start a project like 2 years ago, and we are pretty close to continue this project doing several other new things. I'm also pretty happy to see here Angeli. I taught Angeli at my time at the University of Nevada, Reno, the construction class materials, and also Javier, who was my student in Costa Rica. So thanks a lot for the invitation. I'm going to talk a little bit about the experiment, the first stage of the full-scale accelerated pavement test that we've performed in Costa Rica for the last 6 years. But I am also to introduce a bit what are we doing in Costa Rica, just to let you know, because actually I included in the morning a couple of slides, because when I talked to Hassan, he asked me how we get funds and how we shape up the lab. So I included a couple of slides just to let you know how we work over there right now. We call it the PAVE Lab. This is how we call our accelerated pavement experiment. Well, and those are the two professors that helped me a bit with the presentation. Just to give a little bit of geographic information, I am from Costa Rica. It's here, right in the middle of the continent of Americas. You know, we have 30,000. Central America is about 600,000 square kilometers, 3 million of people. Panama and Costa Rica are the most developed countries in the region. Right now, Panama economically is much better than us, but still in education and social health, we are better than that. Talking to Costa Rica, we are 52,000 square kilometers. Just to have in mind, Texas is 700,000 and Mexico is 2 million, so we are a really small country. Right now we are 4.5 million of people. 500,000 are immigrants from Nicaragua, basically. We don't have armies in 1948. Our main industry right now is the tourism. You see, we are 4.5 million, and we are receiving around 3 million of people a year for tourism. We have the biggest Intel facility in the world. I don't know if you know that. It was established in 1997. So basically, besides tourism, we have a huge income due to, to chips, microchips, and all this type of technologies that Intel is developing around the world. And for the second time, in 2017, we are the happiest country in the world. This is very important. Okay. The University of Costa Rica, we have 240 academic options, so bachelor's, license, master's program. We have 480 grad programs at the university. We have 257 international agreements. Actually, we are working on that in one of them with Dr. Errol Tutunluer. There is a little bit more than that, but like 40,000 students, undergrads, and 3,000 grads. And we are the number 3 university between Mexico and Panama and the Caribbean area. The first one is the UNAM in Mexico, DF. The second one is the Technical Institute of Monterrey. And the third one is the University of Costa Rica. We are like in Latin America, we range between the 16 and the 21, depending on the type of ranking. And we are among the best 500 universities in the world, depending on the ranking, but I think it's pretty good for the university. My program, the program that I am leading, we belong to what we call LANAME, UCR. LANAME is the National Laboratory of Materials and Structural Models. I have to say that one of the developers of the lab was a University of Illinois graduate, Dr. Guillermo Santana. Actually, right now he's like in the Board of Regents of the university. He made his PhD in the 70s and 80s. PITRA is the transportation program that I am leading since 2010. And it was founded in 1997. And we have like 70 workers. This is the worker plus the research assistants. And we have all those working departments. Like we have technical auditing, road network evaluation, specifications. All the specs in Costa Rica are made by us. The government has to validate it, but basically the work is performed by us. It's 10 different specification manuals. Material and pavements is my area, and is what I'm going to talk about. Road safety and transportation. Municipalities, we have a lot of local government work with the very local governments in Costa Rica. Special projects basically is a unit that works for selling services. I have to point out something here. We don't sell services that compete against private companies. We do, when you have a more delicate work and they have questions or they want to develop a new product, they go to our lab. And 2 years ago, we established a sustainability and resilience group that has been working with Hassan and Dr. Al-Qadi for the last 2 years, developing life cycle analysis and everything related to sustainability of roads. That is very important, and in Costa Rica it's very important because we are sort of a green country, and we have developed a lot of work protecting our national forest. I don't know, you might not now know that, but in the 70s we have the forest coverage was reduced to 20% of the area, and right now it's 51%. So Costa Rica is basically one of the few countries in the world that have gained back the forest coverage of the country. So it was very important public policy back in the 70s and 80s, and this is the reason all the preservation of the nature has been very important to our country. So this is my group. Usually it's like half and a half women and men, because this is very important now. And I'm going to say about a little bit, by law, we are the National Laboratory of Materials and Structures. It was a law from 1996. It was an agreement with the Inter-American Development Bank. It was $1 million that they gave us. But for a lot of years, we've been the more profitable investment of this bank. Because, you know, with this seed of $1 million, we have done a lot of more things I'm going to show you. 1997, when I started as a research assistant, this is what we had. Basically, the Marshall hammer, a couple of viscometers, and one penetrometer. This is when at the beginning, our lab was more thought of a structural lab. But suddenly, the humble pavement guys start working, and we developed what I'm going to show you. But at the beginning, the idea was structure, was not pavements. So this is what we had in pavements, and we started working from that at that time. So it happened in 1997. Our national road network was in pretty bad condition. So we started helping and receiving money from the government to improve the conditions. Right now, in the national road network, you don't see this type of stresses. So in 2002, this new law, the 8114, start giving us money. So we receive 1% of the fuel tax. The fuel tax in Costa Rica is 30% of the fuel cost. So it's basically like, it varies from year to year, but between 8 to 9 million of dollars a year for doing various things that I'm going to show you. Auditing projects, we have a group, as I mentioned, only in auditing projects, other in applied research, technology transfer, and accreditation of technicians and engineers, evaluation of the national road network. We evaluate the national road network every 2 years with falling weight, IRI, number, imaging, all these type of devices, local government assessment or help. We can help the Minister of Transportation if the minister has some question, we can help technically. Evaluation of bridges as well, and all the standards. So we receive this money to do all those works. Right now we have 6 PhDs working with us, 3 PhD students and 20 masters from several universities around the world. So not only from Costa Rica, so we have people, some of us start going to study abroad like 20 years ago, 10 years ago, and all those people has returned to the lab work. And right now we have, as I mentioned, like 50 RA per year. This is we have a picture every year. And in the group, most of us are civil engineers, but we have chemists and chemical engineers that gave us, all this knowledge to understand some things that we don't have the background. We have land surveyors, we have also a PhD in geology, we have geographists, and unfortunately, we also have a couple of lawyers working with us. We have, yeah. So those are our assistants right now. I didn't put them up, but right now we have like 15 former students making masters and PhD all over the world. Europe, a couple in Brazil, and like 8 of them in the United States. So we are working in-house, so in the lab, we can see the various phases of the materials, and it was planned like that. So this is an actual picture of our AFM microscope, atomic force microscope we have. Actually, this image is the first image that we took of an asphalt in a size of 20 times 20 micros. So this is when we start trying to understand what's happening on this nanoscale. Well, we can do all the micro testing that you know, rheology and all this type of tests. We have all the performance normals tests, the performance for HMA or concrete or granular basis, all those things, and full scale testing. So the idea is a little bit philosophical. But we are trying to relate everything. We are seeing the properties at this scale. Right now we haven't linked everything, but we have the data. We have the data, for example, of the asphalt here, and we have what happened to this same asphalt at the full scale test. So we are trying to link everything, what is happening, so how the properties are changing, how the nanoscale properties relate to the full scale properties. We are doing some research about that. For example, with Dr. Kim, not the old, the young one, we are trying to develop some analysis here with FAM, and we are trying to see how we relate the FAM with the full scale test. We are doing several things. We are now playing with the data. We are working on all those things right now: nanoscale, moisture damage, HMA testing, PCC, recycling materials, a lot of recycled materials, stabilized materials, oxidation, full scale testing, LCA, pavement design, and software development. This is an image of a crack in asphalt. You see here, this is 15 micros. And we developed this. This is covered by gold. There is a special process to cover the sample with gold during a night, and you can see really what is the size of the crack and what is happening around with the morphology of the sample. I'm not expert in that, but we have people that know, the chemists know a lot about that. And this is, I was talking before about that, is some of the oxidation analysis and research that we are doing, starting from the knit binder and all the katana phase, the per phase, the sol phase, and how this morphology is changing after some environmental aging. This is, for example, in this case, 6 months of aging under environmental conditions exposed to the air and to our raining. So we are doing some oxidation in a special machine we have, a little bit similar to the one you have here. And also we have a lot of samples in the roof of our building, aged with the time to see what is happening. And as we are also working with surface energy measurements. And let me talk right now about what we are supposed to talk about, accelerated pavement testing. This is the device that we have. We have the Dynatest Mark 6 heavy vehicle simulator. We bought it in 2012 after 3 years of thinking about what to do, because we need to sit down. We sat down and think what was the best machine that suit our needs, and also the type of experiments that we were going to do. We received, I have to say, a lot of help from the South African guys, Lou du Plessis, Maurice de Beer, Nick Kotsia, to shape the experiment. Because I think we've been very successful, and well, Dr. Alcade knows right now at the APT committee of the TRB, we are playing a good role, I think, for a new program, because what we have is 6 years only doing that. But I have to say, we receive a lot of help at the beginning from people that have done those tests for 40 years, just to know exactly what to do. Also, Vinan Stein, I know Vinan, they help us a lot. They went to Costa Rica 3 times to teach us how to do this test. We are passing 20,000 bidirectional road repetitions per day. We are working at 10 kilometers per hour. We are applying 5 different loads in each one of the test tracks. Well, this is the type of tire. We are applying wheel wandering. We can apply dry and wet conditions, and basically we are working like 6 days a week. We just stop the machine like on Friday to do some preventive maintenance, once a month to do some stronger maintenance. Every 3 months we stop like 3 days to do an overall maintenance. Basically the machine is working 24 hours a day. It's very important, in order to have a cost-effective experiment. Um, we are working in moisture. Moisture is very important for us. So this is the reason we developed a full facility in order to have the groundwater table simulated and also training. And this is the reason, you know. Let me show you that. Where we have the less rain is 1,200 millimeters a year. But the average of the country is almost 5,000 millimeters a year. But we have places when we have 8,000 millimeters of rain a year. What is allowed, 8 meters of rain. So we need to simulate this pretty well. When we were starting doing the dynamic testing on the saturation levels for granular bases and soils, we start doing all the cores and all the from dry to wet, but we start meeting the geotechnical guys, the professors, and they told us, Luis, we always have 80% of saturation for the whole year. And this is mostly for, even in the drier part of the country, we have the soils and we have the granular bases, well, basically the soil, the subgrade, full saturated, or very saturated. So these are things that we need to consider into our design, because basically what Latin America has done is to copy others' design methods without calibration. And this is when we start having very bad pavement performance. As Dr. Alcadi mentioned, unfortunately, I've been hired to go to projects in other countries, not only in Costa Rica, where you see a pavement fail in 1 year, pretty badly. I'm talking about projects of $100 million, $200 million. This is also money here. And the pavement fail. Why? Because they don't have good material characterization, they don't have fundamental tests, and they don't have a good guide for design. Or the guide that they are using is not calibrated for their conditions. So we have these rainforest conditions, but if you go to Peru or Bolivia, you have also, you have the ultraviolet rays of the sun hitting in a very different way than other parts of the world. So, and there is no research about that, or a lot of research about that. So you can see in Bolivia or in Peru, a hot mix asphalt pavement failing very quick, only because this oxidation. So we need to develop research specialized for those conditions as well. The numbers, we have passed with this experiment 9 million of low repetitions, around 75 million of easels, and 16 text sections. I'm going to show you that. We select 4 different pavement structures, the typical pavement structures in Costa Rica, the normal ones. We have a lot of experience in granular materials, and we have used a lot of symmetrical bases, and I think with very good performance. So we select these 2 asphalt thicknesses, 7 centimeters and 12 centimeters, and we are going to add in white because basically it's what we have. And the second thing, we want to destroy the sections. We can put here the best pavement and have minimum repetition and nothing happens. So it is not going to give us information. So we designed something that is typical for Costa Rica, but we were going to be able to fail it under test, because we want data to see what is happening, how the moduli change. Evaluate construction practices, yes, we did it. It was pretty funny. The last 2 sections, when we have the truck dumping the HMA, we have to use shovels to move it. It basically was cold. But it's pretty common in Costa Rica, so we were not afraid about that. And calibrate our own CRME, the Costa Rican Empirical Pavement Design Guide, that is almost ready. The calibration, because the software is basically already developed. This is the plan. We did this model 2 years before we received the machine. So basically, we planned, we designed this test place. This is like a swimming pool. We have here filters. We put the subgrade. The geotechnical guys didn't like this because we had to touch the subgrade, but we don't have another option. Because if we use the natural subgrade as it is, you have the ground water table moving all the time, because in Costa Rica you have a lot of rain, so you have infiltration, no matter what. So we need to have a very sealed test pit in order to avoid infiltration from the water from the outside. And as well, this is the drawings. We have actual, construction machines, the regular ones. So we were sure that this is exactly how the roads appear in field. And finally, we had everything ready to perform the test. This part of the building, this is the new building that we built, was designed only for this experiment. Click on the figure. This is the HVS working.
How long are your test sections?
It depends, at least 3 months. One of them is like, it took at least 6 months. But we are learning. The idea is not having so much time. But the cement-treated base with the 12 centimeters, basically nothing happened to it. You see the HMA, I'm going to show you something. The moduli of the HMA didn't change after 20 million of easels.
Is that 8 meter long?
Excuse me?
The length?
The length, the full length is like 8 meters, but the real test length is 6 meters, plus times 1.2 meters wide. This is the dead man cable. If something happens, you just go up, push it, and everything stops. Okay. Well, these are the sections. As I mentioned, we have the sub base is the same size, it's like 35 centimeters. We have cement-treated base, and granular base. And thin and thick. Well, thick for our condition, because I know that in the United States, thick HMA is thicker than that. Okay, so those are the sections. We have 2 sections we can perform two tests per pavement. Those 2 are 12 centimeters on top of cement treated. This is 12 centimeters, sorry, and this one is 7 centimeters. This is cement treated base, this is granular base, and this is the saturation chamber, where we can change the groundwater level. This is the instrumentation. I'm not going to talk about that a lot. I'll show you the results. In each section, we have MDDs. When we have granular base, we have asphalt strain gauges placed in with this configuration, horizontally, well, transfer and longitudinally. We have a temperature probe here, and we have a pressure cell on top on the subgrade, and those are the MDDs. We also every day perform the RSD measurement, the road surface deflectometer. So basically we can have 3 measurements for deflection, the falling weight at the beginning and at the end. Every day the RSD, and every day also the MDDs. If you tell me, look, what have you done with this data? Not much yet. I'm going to show you some, but there is a lot of things that we haven't studied yet, because it's a lot of data, millions and millions and millions of data that we can. Let me see, for layer, just to show you this, the saturation. In general, when we apply saturation, we have 70 centimeters of constant water table. The subgrade saturation is around 80%, is normal, and for suction, the base and the subgrades reach a constant value of 43%. You can see here how we monitor the saturation through the millions of easels studied in the test. So basically, you see, it's pretty steady through this time. We can, if we don't do that like that, as we design the test pit, we are going to have a lot of fluctuation on that. Okay, so 5-year summary. We have performed the 8th section that I already showed you, wet and high conditions. 2 sections related to maintenance techniques, cold mix patching and surface treatments. We have performed 2 tests related to road safety, retroreflectivity of painting. I'll show you just some pictures, and performance of raised pavement markers. This experiment was paid by 3M and all those painting companies, and to test with interlock blocks or pavers. I'm going to show you, actually this experiment, the last one, was paid by a private company. I was telling to Jeff about that. It was a fun experiment. I say funny because I told Jeff, Costa Rica built in the Caribbean Sea an artificial island for a harbor, for a port. And they are using interlocking blocks. But the company, the concessionary is from the Netherlands. So the guy said, we are going, so the guy, the consultant company, you have to use Netherlands sand. And it was very expensive. You have to ship it with that. Ships and everything. So the company said, okay, the guys that won the bid, we are going to try in this lab the Netherlands sand against 2 Costa Rican sands. So they build everything, they pay for the experiment, and at the end, you know, the 2 Costa Rican sands behaved better than the Netherlands ones. So at the end, the harbor was made with the Costa Rican sand. Another use of the accelerated pavement testing. Because in 2 months, you have everything, and you avoid to spend a lot of money, you know, bringing this, you know, doing whatever you want to do, and it may not be correct. So this is a quick summary. I'm not going to go in detail. As I mentioned before, we have almost 10.5 loading cycles, and regarding easels, almost 76 millions of easels in the various test sections and in the various experiments that we have performed. Again, we wanted to have it working almost every day. In my case, as I've been like the head of the program, I like to see the machine working almost every day, because otherwise it's not like cost effective. We wanted to do a lot of work. We are doing a lot of Visual Basic programming to collect all this data, because it's a lot. Actually, well, all of you that have worked with the Atlas, you know, to have good databases is very important for accelerated pavement testing. Otherwise, if somebody take the data 10 years after, if the database is not well designed, you are not going to dig out any good information. So you need to be very clear about that. So we are working a lot in that. Symmetry of the base, granular base. Just a quick picture of what happened at the end of the loading cycle. For this, we passed 10 million of repetitions. For this, we reached almost 1 million. Here we have all type of distresses. Here, of course, we have cracks. You see here, you can see the crack because we put water on top of it just to show it. But I'm going to show the results in a few minutes. But, you know, we start taking pictures, studying what happened here, or trying to relate this to the strains reported, to the stresses in the subgrade, and, you know, all the distresses. But this is interesting. I have this picture here because I want to show you something later. For example, some data. The initial falling weight data. What happened to each one of the sections? This is the highest deflation. This corresponds to the weakest section. You know, the 7 centimeter on HMA on top of the granular base. And of course, this one is the stronger one with 12 centimeters HMA on top of the cemented base. And we can do several things. This is the initial back calculation of the moduli using the falling weight. You know, the FAA, they have a machine, you know, a little bigger than us, but they have a lot of money. So, you know, we can use the falling weight at the beginning of the experiment because we cannot put it below. But the FAA, they have their HPS can raise up every day, so they move it up and they put below the falling weight. It's pretty fun. This is the reason we have the RST, the road surface effectometer. to perform everyday deflection basis analysis and compare it to the MDTs, but in fact give us exactly the deflection at each layer. We have lasers here to measure the rotting, and to measure the IRI. You can say this is not really IRI, yes, because the section is pretty small, but we are calculating using the quarter of car model also the IRI. This is what I wanted to show you. This is the HMA, one of the sections. HMA on top of the CTV. And this is how we calculate the model every day, to the reaching 20 million of visuals. And this is the same thing on top of the granular base, and we reach here 1 million of visuals. So you see, it's much less here. But what I want to show is this. See? Basically, to the HMA, it didn't show a lot of distress. Basically, nothing happened to the moduli of the HMA, but the one that is really taking the damage is the symmetry base. See that? And the South Africans developed the incremental recursive design method, where they account exactly by the moduli of the material at each moment or at each time. So basically, it's like to have this. At every moment, you know what is going to be the moduli of your material. We are not that far yet. But what I realize is I cannot design a CTV with this moduli at the beginning, because it is going to last just a few low repetitions relatively to the whole life of the paper. So we are now trying to develop a criteria here to have it here. If you see, this is the granular base, the sub-base, sorry, this green one. At the end of the life, still the symmetric base has a much better moduli. It's different material still. And what is good is also the properties of the sub-base and the subgrade didn't change much. So it provides a lot of information regarding the pavement performance. If you see the granular base, the HMA, well, this is log scale, the HMA reduced the moduli with the time, but if you see the granular base also is being destroyed with the time. You can see here that almost the difference is not like much, because this is logarithmic, the difference is important. This is dry conditions. When you have wet conditions, you can see the HMA coming down very badly. I'm going to show you something later. Yes?
I'm curious about what you've back calculated for the modulus of the granular base. It seems really high.
Here or here?
The red.
This is actually,
Something's not right.
no, this is, yeah, you're right, this is symmetrical base.
Okay.
Yeah, this is a symmetrical base, yeah. This is symmetrical base with the 7 centimeter HMA, with the 7 centimeter, exactly, yeah. Thanks for that, yeah. This is the symmetrical base with the 7 centimeter HMA. So you see the reduction here, and also, again, the reduction, yeah. Okay, we are not sure about this result, but we are sure about a little bit about this result about the subgrades.
Subgrade in the model.
Yeah, this is the subgrade, yeah. As I mentioned, we are not sure about this, but we are pretty sure about that.
Yeah, but as it softens, the CTV, then effectively, maybe your subgrade is softening too, so
Yeah,
stress states are increasing.
yeah, okay. This is permanent deformation. This is I'm pretty sure about that. This is the HMA on top of the CTV. You see the HMA has permanent deformation, but if you see the other layers, the deformation is like pretty low, sorry, because basically the CTV is like controlling the deformation of the underneath layers. And in this case, this is the HMA on granular basis. Basically, all of them start having like also permanent deformation. In this case, this is the 12 centimeters HMA. Also, this is the 12 centimeters HMA. What happened regarding the permanent deformation? Again, this is the full set of experiments with the dry conditions and the wet conditions. I'm not going into details of each one. For example, you can see here, this is the dry condition and CTV, the green one. Basically, it doesn't have, actually, this experiment, we have to stop it. Because we have, I don't remember, like 2 millimeters of permanent deformation. So at close to 20 millions of easels, we stop the experiment. Now let's see this, the other extreme, is this one. This is the granular material, this one, with the 7 centimeter HMA under wet conditions. So we have like a lot of data to play to see the performance of various sections. At the end, I'm going to show you how we're using this to calibrate our ME. The stress of the subgrade, we are not very sure about what's happening here, but for example, this is the stress of the subgrade for this section, for the 12 centimeters HMA on top of the CTV. Did you see? Basically nothing happened. Not much. It increased a little bit but after a while it started getting constant. And again, we are not sure really about this, but those are sections. This is AC1, is the 7 centimeters HMA on top of the CTV, and this one is AC2, is 7 centimeter HMA on top of the granular base.
On the AC1, does that 2 million easel level, does that correlate with when you started seeing quite a bit of cracking in the base?
Yeah, I think so. Yeah, exactly. Yeah. Okay. Actually, I have to say something about cracking. In the granular base, you see a lot after some moment. But to see it, we need like to paint with water a little bit. You know, we throw some water just to see the cracks, because otherwise, with the cement treated base, you don't see anything. You need to do something. Now we are trying to, with cameras, you know, like infrared or something, to see if we see something for the cement treated bases. I'm not going to, we haven't really do a lot of things with this information. This is the MDD data in 2 different locations. The difference among it, because the depths are different, but those are the current deflection basin in 2 different positions of the test track. We use it before to do some back calculation. We compare this against the falling weight and against the RSD. I have a slide about that, but we haven't done yet a lot of things with this information, but we have this for every day for all the test sections. The moduli, how change with the ease of repetition. This is the permanent deformation for 2 of the cases. For example, this is the permanent deformation for AC1 on the dry condition. And this is the same test track under wet condition. You see, it is a lot. There is a moment, like 2 moments here, everything comes like constant. We have like a second. I'm not going to say that this is the second flow stage, but you know, it's sort of. And there is a moment when it becomes very bad. When you have water, in compared when you have dry conditions. And those are the moduli for all the data, how the moduli are changing with the time. All of them. And how it, for example, these red ones is the CTV on the dry and wet conditions. This is the dry condition, this is the CTV for wet conditions, and this is, for example, the HMA wet, and this is the HMA on the dry conditions. So we are doing a lot of analysis trying to understand all those behaviors from all the others. You can see here dramatically what happened with the subbase. This is the dry subbase, and this is the subgrade, sorry, and this is the wet subgrade. So how the moduli change with this condition. We are using the normalized area ratio, you know, the falling weight, the indicators. For example, this against, we start plugging things to see what happens. So you see, this is the permanent deformation, and this is the normalized area ratio. In this case, this is the thin HMA on CTV on the dry conditions, this one, you can see, we start seeing here shear deformation for the mix. And you can see the permanent deformation very, very badly. And here we have the other various behaviors. For the normalized area ratio, if you are here going into this direction, the performance is the worst. So we are trying, do you remember these parameters? So I think were developed in South Africa. We are trying to develop, to validate the specs that they have or to do some specs for us. Here we have the other parameter, the radius of curvature, and you can see some trends, various trends. For example, here the bigger is the best, so at the beginning, I don't know, I'm going to talk about this. This blue one is the thin HMA on top of the granular base under wet conditions, and how it decreased the modeling with time. And this is the same with the, but under wet conditions. So we are analyzing all of them. This one is pretty interesting. This is the normalized area ratio versus the zero, the normal parameter that we use for using polywet data. You can have here two different behaviors. This one here, those are the dry, and those are all the wet results. So we found like sort of a trend, and the data like go together, you know. This is, as I mentioned, those are the wet conditions, those are the dry conditions. And what is funny is that everything is like continuing. No, we are not sure about that, but we think that we might extrapolate things about this behavior. If you tell me exactly what right now, we don't know yet. We are thinking. But at least it's interesting we have this difference. It was funny to find this difference among wet and dry. And how you have a section here, and the other is like in the same pattern. So it was interesting. The IRI, those peaks are the wet conditions. The other behavior are the dry conditions. So as I mentioned again, because some people has argued about this before, this is not exactly the IRI that we mentioned. So the section is only 6 meters, but we use the same quarter of car model to calculate it. So you can see, for example, this section, this is again the thin HMA on top of the granular base under wet conditions. You see it is behaving well, and there is a moment when it starts picking. Part of what we are doing with this data is to calibrate some performance model, going from the lab to the field or to the accelerated pavement testing. So, for example, we are calibrating this transfer function for the 4-point bending beam. All of you know that. For plant mix and for lab produce, we have several data to do that. And we are trying to correlate this with actual, our test sections fatigue mode. We are using the concept of the damage, basically how the response is reduced with the time, using this damage idea regarding the low repetition in the 4-point bending beam, and try to relate the same concept to what happened in the field measurements, since we have the moduli every day. So at the end, for both the plant produced mix and the lab produced mix, we have a model of damage. We'll do some statistics to see that everything was significant or not. We use the data that I already showed you before. We tried to, it was a very small work, it's not published. We tried to see if the moduli that we calculate was correct or not by trying to approach using the 3D mill software, the viscoelastic software that can predict the behavior of the material under certain speeds. We try to correlate with what we predict with the model with the actual measurements of the LVDTs. We also use finite element models using this as a tire footprint that we develop in our lab as well. So at the end, we find some correction factors for the plant produced and for the lab produced mix. I'm going to show you one of the questions here. So at the end, for example, for lab produced mix, we found this general fatigue transfer function using this idea that I already showed you. At the beginning, we were a little bit scared that it was going to give like crazy results, but we compared it against the MEPDG. It works fine. Of course, not the same value, not close, but fine. And we compared to another fatigue models that we think that are more closer to our condition, and it is not giving crazy results. It is giving a good results. As I mentioned, we use several things trying to. This is the only use that we have done to the strain measurements. We haven't done much yet with this, but at least we know that the back calculation model is good because or it's a good approach because we, as I mentioned, we calibrate the horizontal and the longitudinal strains, and we compare it against the back calculation model. We perform the analysis, and the result became pretty good. So we are calibrating this. If you mention, I have to stop. No. As I mentioned, the idea is to calibrate our own CRM. We also calibrate some permanent deformation models for the base and the subgrade. So those are for dry conditions, for dry conditions. Those are for wet, for dry conditions. We also have another ones for wet conditions. So we have the number of repetition, the deviator stress, the confining stress, and this is the optimal percent of water of the sample. And just to finish, some elements related to the development of the test. As I mentioned, the RSD measurements. Those are the cold patches that we study. Also surface treatments. We are measuring some contact pressure study. We already published a couple of papers using this modeling. It's just modeling, but we already know what is happening regarding contact stresses between the tire load and the surface of the pavement. Pressure reflectivity, as I mentioned, we work with thermoplastic and solvent-based paints. These are part of the results. Actually, at the beginning, to me, it was meaningful, but for painting people, it was pretty good result. We use this experiment. We have this. We designed this conditioning chamber with those sprinkles for water and with those ultraviolet and infrared lamps to keep to apply temperature. In Costa Rica, the first experiments we didn't use the chamber, but the temperature for all the experiments was 24 plus minus 4 degrees. So basically, it's pretty stable. But if we want to go up, we have right now this environmental system, but it's pretty good. The lamps has an angle that is close to how the sun rays hit in Costa Rica, and it's a very efficient warming system. So the heating system works pretty well. And see, this is part of the experiments with the raised pavement markers. Basically, they were seeing that the ability how long those could be clean or detached from the surface. We are working a little bit on that. We just started like 1 year ago on ultraviolet aging. As I mentioned, we have, as I mentioned, samples on a rooftop, but we also have this machine that was developed by a chemical engineering student that is working on that a little bit. So we are working in time of exposure, wavelength of the radiation, and temperature. And we are trying to relate this chamber to this chamber. Interlocking blocks, this is the experiment that I already mentioned, the experiment of the people from the Netherlands. But we are doing a second phase, just to be a little bit more, getting into the performance of the interlocking blocks and maybe suggest another design method for them. I know that there are some design methods around, but we want to either validate one, calibrate another one, or develop our own. So right now, a master student is developing a finite element model of that. Maybe in a second phase with another student, we are going to study the experiment, how the movements of the small bricks are, the rotation, translation, the vertical deformation, what happened to the sand layer, all these other things. Oh, well, the second phase, I'm not going to talk more than 1 minute of that. We are working on recycled materials. We've done a lot of work on plastic added to the HMA in 1 or 2%. And also with RAP, my PhD dissertation was in RAP, doing all this cost analysis, life cycle analysis, and to prepare technical specifications. Basically, this is the test setup that we are going to use, say, for 10 centimeter, granular base of 20 centimeter, salt base of 30 centimeter on top of the soil. And we are going to move the equipment to the field. As I mentioned at the beginning, to analyze this, we have developed some software, some applications. We developed this one, it's called Pave. It's for multilinear elastic theory. So basically, it's another software, like all software that you know about that. But right now, it's becoming very popular in Latin America because it's very practical and very user-friendly. The Rigid is an artificial neural network frame that we developed. Actually, the student is here doing a master's degree by Ricardo Quiroz. We developed a huge database on Iceland, and we calculate, we develop a database, and we are trying to interpolate from those results using this concept of artificial neural networks. The Modin is a software for HMA master course development. We already have the second version, and it is very friendly for the users. It has all the concept developed in USA, but also has the Hervé Benedetto ideas of the black space and the Cole chart to see if the material is real viscoelastic or not, and if the material can be really analyzed using the normal shifting or not. And the CRME is our own pavement, empirical mechanistic pavement design guide. Basically, we use all the ideas of the MEPDG. It's a little bit, it's more simple than the MEPDG, but we are including all what we are developing in the various experiments that you already saw into this software. Basically, right now it's only for flexible, but we are also developing it for rigid pavements. We are going to build all those new test sections in Liberia, in the north of Costa Rica, the next 2 years. So here we are going to have everything: concrete, HMA, recycled materials, and other type of things. This is in the University of Costa Rica Northern Campus in Liberia. The building is almost finished. This building is for the lab. So we are going to have more opportunities to do more research. So it was.
Questions? Isaac.
Thank you so much for this nice presentation. I have a small question related to the model. You said that you are working on calibrating a model for the fatigue based on beam fatigue and accelerated pavement testing. So I didn't really get how you're crossing from you're testing a material in the lab to including the structure also in the model. Are you just changing like the response? Because a single response can come, equal response can come from two different structures that will behave differently.
No, it's just a calibration. Just like
why are we assuming that the accelerated pavement testing is actually what will be showing in the field?
No, it's not the same. You have to assume several things just to do that. And this is what you have to do. Otherwise, you have to go through LTPP. So we have to assume things. You have to use the exponential. How do you relate the loads? Because if you see, we start in 40 kilonewtons, but we end in 80 kilonewtons. And this is because we want to accelerate the pavement deterioration. But at the end, we went back and we convert everything into like a single normal easel base. And based on that, we start assuming things to relate one to the other. But of course, it's not the same. It's not the same mechanism. But you need to assume something to have something to design. Otherwise, you know, why we could have done an LTPP. But when I went back to Costa Rica in 2011, I didn't have 20 years to wait. You know, so we have to do something, and we go through this technology. Your question is pretty good. Yes, it's not the same, but we need to correlate somehow. We have written like 3 or 4 papers about what we do. It was not only our idea. You know, we follow a little bit of what the South Africans made before. It's the same thing that they developed like 40, 30 years ago, and it's trying to have something. And you need to design. You need something that you cannot design with the beam fatigue from the lab. So is a correlation factor is raw. It's not like very precise, but at least it's good instead of waiting 20 or 30 years to have all the database of performance and be tracking what happened in the field.
Just one more clarification. So whenever you were showing like how the modulus is degrading, this was based on some back calculation, right?
Yeah.
For each of the layers. So how can we say, like, we know that, for example, for the fatigue, that there will be like a degradation of the modulus that will happen with the load. But how can we know that this degradation is coming from the material itself and not from like the entire structure that is? Because at the end of the day, it's based, this back calculation, on all of the layers. So how can we know that this degradation is actually coming from material degradation and not from like the structure, what's happening and the interaction between all of the layers together?
Well, I think it is what it is. You have this pavement structure, and you are subjecting it to those conditions. So you have to analyze, and you have to analyze the data, and you have to analyze what you have from the raw materials, and you have to analyze what you have from the performance testing before, and it can give you the answer. I cannot give you like a general answer like that, like saying, yes, in this case is the whole thing, or in this case is the one of the specific layers. We were a little bit sure about what was going to happen to the pavement before. But we already know a little bit because we model everything with the traditional methods. But I cannot tell you like that is this rule. In some cases it might be, for example, I'm pretty sure that in the case of the thin layer, it's pretty easy to know that this layer is pretty thin, but for the conditions for the HMA, it's very thin for the conditions that we are subjecting it. You know, mostly when we put water, we know that. Mostly we start simulating raining. But in the other case, I cannot telling you like that. We need to go case by case until what happens.
Marshall?
What was the cement content and compressive strength of your cementary base?
Is 2.5 megapascals, 25 kilograms. I don't know in megapascals. It's 25 kilograms per square centimeter.
Are you doing any work with the fatigue behavior, CTB?
Not yet. We are doing it aside. We develop the test. We have it. We have an MTS and we have all the everything. We have a master thesis that we already did, but we are not happy about the results, so we are not saying anything yet. We are going to repeat this experiment.
That's a very key element. We're working on that issue right now. I have for the past several years. And the fatigue behavior, CTB, is not a settled issue, let's say.
Especially if it's cracked.
All the wet and dry comparisons you showed, I noticed that you're always doing FWD and back calculation showing the modulus degradation. But are you able to run strength tests at different dry, wet conditions. And this applies to not only granular or soils, could apply to even the HMA and cemetery.
No, for the granular, yes. For the subgrade, yes. For the HMA, the normal ones, but not the strength. No, not, actually, no, we did it. No, actually, we have a paper, now we have, for example, the,
TSR stuff.
no, for the dynamic modulus, we have addressed it. We presented 2 papers at TLB. So we subjected it to various, moisture damage cycles, not only to the one, and we have the dynamic modulus. And we have also the TSR, and we have also a MAC. Not only one cycle with, I think we went down to up to six cycles.
So in our experience, really, rutting relates to strength more than modulus. And of course, modulus is a good way to monitor things, but strength really governs.
Okay, thanks a lot.
Any other questions? All right, with that, thank you so much. Schedule this afternoon. The next, I guess, you are meeting with our students, right? So you're gonna rearrange the room, guys?
It's
I'm sorry? It's at 2?
yes, I think he has a meeting now already.
Am I
Oh,
next?
it's with Professor Pitumla,
Great.
because we need time to rearrange the room.
I
So
can
you
take
need
it to
somewhere
my
else.
office.
Yes.
Are you primarily using elastic layer approach? Have you done any work in the area of research contingent behavior, soil variability?
How are you? You may
There are a lot of
ask
sort of
me
things.
You're making it pretty well, yes. Things going
Well,
well.
you're submitting, you have some publication on your submitting.
So what you're doing is that
Yeah, I can send you.